Welcome you all to today's episode of Physics Fundamentals. Now, before jumping into the topic, let me remind you that I have attached an Edpuzzle link in the description and in the comment section of this video. You can access that link in order to have an interactive quiz session while viewing or watching this video. Now, before jumping to today's topic and without much digression, let's start with some connecting points. What's the link between Virat Kohli's spectacular shot, this rocket launch, and Sunil Chhetri's magnificent goal? Well, I believe you have guessed it right. They have all applied some sort of force. Now, what is this force? Is it the amount of weight you can lift? The number of bricks you can break with your bare hands? Well, let's dive deeper into this. In order to understand what is actually a force, we need to learn what is a force. Well, if you consider an object, any push or pull on an object is called a force. That is, a force is defined as a push or pull on an object. Hence, we are coming out to today's topic, which is force and Newton's laws of motion. This Newton's laws of motion would help us to better understand what is force and what we can deal with it. Now, a force is a push or pull on an object. Sounds like a pushing or pulling on a door, but it's not that easy, and it has got a more nuanced structure to it. In order for a better understanding of it, we need to know about three laws regarding it. The three laws were given by Sir Isaac Newton. Well, let's jump into the first law. The first law is also called the law of inertia. Inertia comes from a Latin word which means lazy or sluggish. Well, the definition comes out as the law states that an object will remain at rest or in uniform motion in a straight line unless acted by an external force. What does it actually mean? That is, if an object is left idly, it will remain at that idle position. It will sustain that ideal or state of rest until and unless we apply a force on it. So, object is basically saying that leave me alone. Whether it is at rest or is it moving in a uniform motion in a straight line. That's all. That was all that first law has to say. Now, where can we see this first law around us? Let's dive into some application. Suppose I am in a bus or you are in a bus and the bus suddenly starts. We can see that this gentleman moves backward or is jerked backward. Why does this happen? Because when the bus starts to move, the legs are in contact with the bus. However, the upper body portion is still at rest or tries to be at rest. However, since the bus starts moving and our legs are moving with the bus, our body opposes it by its inertia of rest. As a result, it jerks backward. As we can see in this video, like this gentleman moved or jerked backward. In a similar example of it, if we can see a person or this person eating out of the metro, we can see that what our parents are already warning us, don't jump from a moving train. Why? Because you can see that this person, as soon as he jumps out, his legs, which comes first in direct contact with the ground, comes to rest abruptly. However, his upper body is still maintaining the state of motion. Why? Because of inertia. Body at rest or in uniform motion in a straight line continues to be in that state until and unless an external force applies on it. However, we can also see that the person falls down in the direction of the moving train. Why? Because his upper body was moving in that direction before he jumped out of the station. In order for a better demonstration or a household demonstration, we can use a coin and card trick. What we can do here is take a glass, a card and a coin. You can take any playing card, trump card or any card you need, or a debit card if that's the purchase of it. What we can do is place the coin above the card and give the card a good flick. What happens here is that the coin will sustain its inertia of rest and hence will not move along with the card because the force was applied on the card and not on the coin. As a result, according to Newton's first law, the coin should remain where it was. What happens here is the coin would fall down inside the glass and the card would fly away due to the flick. In order to better perform it, I believe you need 2 to 3 trials in it before you become a master or before you become perfect in that. In that video, we can see that this person places a coin on the card and gives the card a good flick. The coin then just drops down into the glass. Now, let's move on to the second law. The first law stated with what we can say a qualitative aspect of force, that until and unless a force is applied on an object, that object will stay or sustain its state of motion as it was, whether the motion was rest or the motion was moving around in a uniform straight line. The second law deals with how we can measure that force. I mean, we are studying physics, so we need to measure something. So the second law tells us that force on an object equals the rate of change of momentum with respect to time. We have got 2 terms here. We have momentum and time. For those who don't know what a momentum is a product of mass and velocity, represented by the letter P, small p. P is equals to m into v. For those who are well versed with calculus, they can instantly understand that this is a differential symbol, F is equals to ddt of P. For those who are not, ignore the d's. What we have is the force is equals to momentum by time. P is the momentum here and T is the time. And we all know that mass is a constant here, so it will move out and we would get V by T, which is nothing but acceleration. So it boils down that we have force is equals to mass into acceleration. That's an easy statement, right? Now, we have studied about the qualitative aspect of force. We have studied about the quantitative aspect of force, which is how we measure force, mass into acceleration. Now, the final or the third leg of this laws would be to better understand the property of a force and how the force comes about. I believe you all have somewhere or another heard this law, which is the Newton's third law, the famous Newton's third law. For every action, there is an equal and opposite reaction. What matters here is that we can see in this picture that this person is pushing the wall. All right. Here, action and reaction, or the opposite reaction, or the action and reaction, are both forces. We can visualize it like if you are pushing a wall, the wall is not moving, right? But you are applying a force. So where does that force go? In physics, the terms just don't vaporize. There are solid reasons behind having no application or no visualization, right? This force doesn't go. It is counteracted by another force of equal magnitude, but in the opposite direction, right? That force is called reaction. So what we are doing is we are pushing the wall, which is our action here, and the wall is again pushing us at the same magnitude in the opposite direction. As a result, these 2 forces balances each other and there are no net force. As a result, we can see that the wall is not moving, right? We are not moving the wall. However, always remember that this law is more nuanced and it is very easy to have a conceptual holes in it. In order to have a solid foundation, always remember that this force always occurs in pairs. Like we can't have the action alone separated out and the reaction separated out in different containers. We can't have that. Action and reaction always occur simultaneously and they are always opposite to each other and have the same magnitude. Right? 3 properties. Simultaneous, equal magnitude, opposite direction. Also, they act on different bodies, right? They act on different bodies. When I am pushing the wall, action is on the wall. When the wall is pushing me, the action is on me. 2 different bodies, right? Now, well, we have understood that the Newton's third law consists of 2 forces, action and reaction. Both are pushing each other, 2 different objects, right? What applications can we see? Suppose we have a rocket launch. What we have here is that the rocket is moving, right? The rocket is moving upwards What happens here, if we consider that the motion of the rocket moving upward is the action, there must be a reaction. Now, since the rocket is moving upward, force, it must be exerting or experiencing a force upward. The reaction must be same magnitude, opposite direction, downward, different bodies, not on the rocket, right? Here, the reaction is a burning of the rocket fuel. What is it? The burning of the rocket fuel. The rocket fuel is pushed downwards. As a result, it pushes the rocket upwards. It is the reason why rocket fuel, or the what we can say is the management of rocket fuel or the efficiency of rocket fuel, is one of the most important aspect of construction of rocket and of rocket science. The same thing also occurs when we are firing a gun. Here, what happens is the bullet is moving out of this muzzle at a great speed, right? So a bullet is thrown out, a force is applied on the bullet, it is moving out of this muzzle here, we can see. Due to the Newton's third law, it must apply a similar force, equal magnitude and opposite direction on the gun itself. However, we don't see the gun moving out at the bullet speed, right? Why does it happen? We know that force is equals to mass into acceleration. The bullet is having a very large acceleration and a very small mass, right? Small mass, higher acceleration. The gun has got a very large mass compared to the bullet. As a result, its acceleration is quite manageable. It's quite manageable. It does not yeet out like a bullet. However, when we are those who have fired a gun, I believe there are very few of it. While firing a gun, it is always and always we have to make sure that the rear end of the gun is attached to our shoulder. It is touched. It is in contact with our shoulder. If not, you will be left with a dislocated shoulder. Because because the gun is jerked backward with so much force that it can easily break your collarbone or can dislocate your shoulders. If you don't want that, just keep the rear end of the gun or the what it is called a stock in contact with the shoulder. This is also a great example of Newton's third law. This person is pushing the ball in forward. However, the person himself is moving backward. Well, if the person is moving backward, someone must have pushed the person backward. But we can't see anywhere else, right? Anybody else is there and nobody is pulling that person. What happens is, when the person pushes or throws the ball in the forward direction, he or she, any person, applies a force in it, which would be our action here. The ball in turn causes a reaction force or gives a reaction force to the person, and the person moves backward. So the reaction force is what makes a person move backward on the skateboard. Here too we can see the similar example or similar analogy, that the ball moves in a much farther direction compared to the person. Why? Ball has got a very small mass. As a result, it has got a higher acceleration for a given amount of force. The person has got a very high mass and a very small acceleration. As a result, it moves to a very small distance. Now, let's consider an example. We have an earth here, we have an apple here. I have taken the apple intentionally due to this being a little slow. We have an earth here and we have the apple here. Now, according to Newton's third law, there is always an action-reaction pair coming up simultaneously. Consider that apple falling downwards. Why? Gravitational force of the earth, which is still a force. So, if the apple is pushed downward, apple is being pulled downwards, according to Newton's third law, there must be a reaction force caused by the apple on the earth, and the apple should push or should pull the earth upward towards it. That means that the earth is pulling the apple towards it. That's observable. But do we observe an apple pulling the earth? No. Sounds absurd, right? Why is it absurd? Because laws of physics don't care about the magnitude of objects we are taking. They are ruthless in that sense. However, that also makes them universal, so we can't complain. Now, alright, let's Give it a shot that yes, the apple is pulling the earth somehow. Apple is pulling the earth. How much? We can't see the earth moving, right? How much is it? If you calculate it, the distance comes out to be 10 power minus 26 meter. That is 1 by 1 followed by 26 zeros. 1 by followed by 1 followed by 26 zeros. Do you know how much is it? This number is so small, so small that it is much smaller than an atom. It is much smaller than an atom. Not much smaller than an atom. As a result, we can't see it. Now, enough with that philosophical talk about force. Let's measure force. How do we measure it? We take the help of Newton's second law of motion, which is the quantitative aspect of force. Force is measured in newtons and is represented as N. Newtons, obviously, after Sir Isaac Newton. Now, we already know that F is equals to mass into acceleration. Mass is measured in kilograms, kg. Acceleration is measured in meter per second square. Hence, 1 Newton is equal to 1 kg meter per second square. That's the formal definition. Well, how can we visualize it? 1 Newton is that force which pushes a object of 1 kg with an acceleration of 1 meter per second square. 1 kg with an acceleration of 1 meter per second square, and you can get a force of 1 Newton. But how can we make sure that we are experiencing 1 Newton of force? Well, to put into perspective, let's get some practical applications or practical visualization for that same. We have a bottle of water and I want to lift that. How much force am I applying? 10 newtons. An average kick to a football? How much force? It's 50 newtons. A standing adult. Standing adult exerts a force on the ground, right? Due to its weight. Due to his or her weight. How much force are we applying? It's 500 newtons. Well, we have a constant upgradation on force. SpaceX Falcon 9 rocket launch. How much force are we applying? Take your best guess. How much would be? A standing adult is 500 newtons. SpaceX Falcon 9 rocket is tons of weight. So it must be what? 5 lakh newtons? 10 lakh newtons? For that's it. Well, you're close enough. It's 76 lakh newtons. It's a great force for that respect. Now, I believe for one lecture, for one episode, we have understood enough about force. In order to summarize it so that it gets into your head, well, we started with a definition of force, which is a push or pull on an object. However, that definition of force sounded like we are pushing or pulling a door. For a better understanding of it, we need to learn about Newton's laws of motion. We have got 3 laws. The first law being an object remain at rest or in a uniform state of motion in a straight line until and unless it is acted by an external force. Leaves the object as it is. The second gave us a quantitative aspect of force, which gave us a formal definition of force or the measurable definition of force being a product of mass into acceleration. The third, or the famous law that for every action there is an equal and opposite reaction, helped us to understand the phenomena surrounding that force. Now, understand one thing. These 3 forces are of philosophical in nature. Right? That's why in that time, or in the Newton's era, scientists were called philosophers. They were not called scientists, they were philosophers. One gave the qualitative aspect of force, second gave the quantitative, and third gave a property of force and how we can visualize that, right? So it is a philosophical sentiment attached to it. As a result, don't go about proving first law from second law or third law from second law. No, it doesn't work like that. It has got their own philosophical gravitas of its own. Fine? Now we have understood the applications. These applications were already interspersed within that presentation. And finally, we understood about the Newtons of law, units of force, which were its own definition and perspective. And I believe that will be all for today's lecture. for one episode, it will be all Philip 1. So stay tuned for your next episode in order to better understand when I come up with the next episode of Physics Fundamentals.